Hi, everyone. My name is Paul Bemis. I'm here with Dru Crawley today. We're going to be talking about building decarbonization. This is a big issue for us all. This is a part of the energy transition that we're going through. We see this in our daily lives. We see this in the newspaper every day, the cost of energy, the whole situation going on in Europe with the invasion of Ukraine, driving up energy prices. The global warming issues that we're facing, how do we address those? How do we get carbon emission down? And we know, those of us in ASHRAE know that buildings contribute to upwards of 40% of total carbon dioxide contribution to the atmosphere, both in the building of them, the creation of them, and the operation of them. So buildings are a big one. And with the growth that we're expecting in population and with the old stock that we have in terms of buildings, existing inventory, we have to take a step forward and figure out how we're going to accelerate this transition to reduction in carbon dioxide transmission or emission as rapidly as we possibly can. And to that end, I have to give ASHRAE credit. ASHRAE, as a global organization, has started a decarbonization initiative and task force and is focused on this topic. And today we're lucky to have Dru Crawley. Dru is a person who's been involved with buildings and building design and energy efficiency for probably most of his adult life, Dru, I would say.
Yep.
Yeah. So he has been involved with the Department of Energy for many, many years, worked on modeling, energy modeling, and using Energy Plus or management and creation of tools like Energy Plus. He currently works for Bentley. Bentley is a construction design software company, primarily known for their CAD products and engineering design products, and is working on this decarbonization effort together with ASHRAE and is here today to talk to us about the task we have at hand and how we can position both ourselves as leaders, ASHRAE as leaders in this effort, and also tangibly, how can we individually have a positive effect on this situation and take action to encourage the movement towards a non-fossil fuel future. So with that, I'm going to hand over to Dru to go ahead and make this presentation today. Just a couple of sort of administrative things here. This is a webinar, so this is a listen only, view only at the moment. Your mics are all muted. However, there is the opportunity to ask questions. You can type them in. There's a little panel, it should be over on your right. Go to webinar panel that popped up when you logged in. You can type in questions. I'll be monitoring the questions, and that will allow Dru to concentrate on his presentation, and he can go ahead and keep going. I will try to ask the question on your behalf at the right time. We'll also try to leave room at the end of the presentation for any kind of discussion or questions that you might like to have. I can unmute occasionally, but it doesn't always work perfectly, so, so please bear with us. And we will get you a copy of the presentation at the end. There'll also be a recording of this broadcast so that if you would like to view it again, you'll be able to do it. That will be delivered to you as an email, an automated email that will come to you after the program ends. So thank you, Dru, and welcome to the program, and I'll hand it over to you.
Great. Thank you, Paul. Let's see here.
Yeah, we can see your display, so that's good.
Okay, great. Okay. Well, thank you, everyone, and thank you for coming on Thursday morning. This is a presentation I actually gave at the Chapters Regional Conference in Concord back, I guess that was August, and been doing this. This is a subset of a longer 3-hour presentation that I give for the ASHRAE Learning Institute. So in some places I'm going to move very fast, just try to get through the material here. But as Paul said, I'm happy to take questions and pretty casual about moving forward. So Paul, if you see something that pops up that's kind of relevant to a particular slide, just let me know.
Yep, sure will.
So, so we're going to talk about how buildings contribute to carbon, understanding what the definitions are, and what ASHRAE is working toward on that. What are the various scopes of carbon and what they include, decarbonization methods and ways it can be implemented, and what ASHRAE has been doing in this. I will say that this, as far as the courses, the 3-hour courses that ASHRAE has been putting together, this is one of 3 that are being assembled for that. So this one, the second one is primarily on what to do specifically in HVAC systems and how we can decarbonize those systems. And the third one is how do we apply it more vigorously throughout everything we're doing. So I'm going to touch on some of those topics, but not spend a lot of time on them. I will say that this is not primarily all my work. I put this together, but I had a lot of help from smart people that have been working on the task force for building decarbonization. And so some of these slides are directly from them. So that's my outline. But I want to give some background starting on this. We're looking at another 2 billion people joining the planet in the next 30 years. And sometime around now till the next couple of weeks, I'm not quite sure exactly when it's going to be, but the 8 billionth person alive will join us here. And so we are already huge growth in population globally, and that is going to continue. The other thing that's going to happen with trying to bring in another 25% growth in the next 30 years, we're going to need buildings. And it's estimated by 2060 we're going to need 230 billion square meters, or 2.3 trillion square feet, which is effectively like building New York City every month. And that is a huge growth area. But it's not going to happen in kind of the traditional areas. There's kind of a terminology of the global north and the global south, and you see the global north is the blue here, and the global south all the red going on. And most of that growth, both in population and in building construction, is in the global south. So that is a large amount of going on. A good chunk of it is going to be in Africa, particularly as economies like Nigeria, which is already Africa's largest economy, is going to grow by 50% over the next 30, 40 years. So it is a huge transition. It's not so much in what you may think of as kind of the traditional parts of the world. On the other hand, we're already seeing huge change in the climate, and that's the reason we're even considering decarbonization. It is the goal that we're trying to deal with, and from 2015 trying to do it from 2 degrees to 1.5 degrees Celsius, but now pushing it to 1.5. Unfortunately, I think we're already going above that if you start looking at some of the data. I have recently did a quick study, just picked 12 cities at random, and we're already seeing about a 0.5 degree change over the last 25 years in our design conditions. And that's kind of disturbing that we're already doing that before what these models are predicting that we're going to move forward. I also like to start my talks about why do we even care about buildings, and it's if you look at worldwide there on the left, you'll see about 30% of our energy use is for buildings. If you go to the far right, in the US, it's even more. It's 40%, and it's growing. But if you look at the third and fourth bars, you kind of see the contrast between a very dynamic developing economy in China, where buildings are only about 20%, and Hong Kong, we're at 65% today. And so Hong Kong is very little industry related. It's all services and banking and other business sort of activity. So
Hey,
buildings are,
Drew, quick question about this chart. You've got here listed industrial, transportation, residential, commercial. When you list transportation there, it's the only one that is not a building sector, right? The other three, when you say that, you're talking about the buildings themselves, correct?
well, yes. And, even industry here, I'm really more talking about the process more than
Right, right.
building, because
So, so if we looked at building footprint alone, it would be residential, commercial as the two components, correct?
yeah, yeah.
Okay, okay.
So it as noted, it's large comparatively, but and for a developing economy like China, you're seeing it. It's already at 20%. Well, 15 years ago when I started putting these together, it was at 12%. So for economies that are growing, that global south, as I showed earlier, huge change in what they're doing and moving forward. But regardless of that, buildings are a large part of that. So,
Right.
if we look at the US, particularly buildings over 40%, about half commercial, half residential, um, and industry at 33%, transportation less. Industry, if we went back to the 1960s, industry would have been not unlike China, well over 50%. Transportation's been growing, but I think we have good quality standards that are really pushing that. The other thing that's happening is our buildings are changing. It's partly the technology that's being adapted. If we look at our houses, you look at the top three and say, well, heating, water heating, cooling, refrigeration, and some of the appliances, that's not a big deal. But at the very bottom, we have this category, which is other uses. These are small things, but these are a lot of technologies that have not, weren't traditionally considered in what we were doing. If I were there live, I'd be showing you my phone and all the computers and all the bits and pieces that are now driving a full quarter of our energy use that weren't there probably 30 years ago. So if we're going to deal with it, we have to deal with the spectrum of what's going on in our buildings, not just the top three or four, which I think is where we've been focusing. Commercial buildings, that other uses is almost a full third. But of course, there's no typical commercial building. If I were a supermarket, that refrigeration category, which is shown a second here, would be over 50%. And then cooling and lighting would be second and third for that. So depending on what type of building we're in, it varies a lot in what we're, excuse me, what we're seeing. But on the other hand, the other uses we have to deal with and being able to look at that.
So, Drew, examples of other uses. You mentioned your cell phone. Other users could be, for example, IT infrastructure, right?
Yeah, definitely.
Well, you've got computing listed.
Some of that,
Mhm.
you see office equipment and computing,
Yeah, I saw that.
which is 13% of the total.
Right.
But it is the IT infrastructure. It is, I don't have anything about elevators and escalators in here, and
Right.
in a lot of buildings, that's a larger building. That's a big percentage of what's going on.
Right. Right.
So, if we look at globally where the carbon is coming, the carbon dioxide equivalent emissions, buildings are responsible for a full 37%. And you see transportation, other industry, and then non-building construction industry, another 10%. If you break that out between residential, non-residential, the indirect amount is related to our electricity, because that is one of the biggest drivers in carbon globally. So buildings, non-residential buildings are responsible for 46%, or almost 20% of that total, not unlike the numbers I was just showing. and the non-residential a bit more. But a quarter of that 37% is in construction, and the materials that we build, the processes we use to get our buildings built today. So it is not an insubstantial amount of energy or carbon emissions here. So why do we even care? Our human-caused emissions have to go to zero by mid-century, by 2050, if we're going to have any chance of trying to limit the human-caused climate change to two degrees. Now, a lot of variability in what's happening there, and that means decarbonization of entire systems, our buildings. It's a huge amount of work that we've got to do. Already, a lot of places are already committing to that, not the US particularly, but trying to get to a net zero net carbon is a huge challenge for that. But if we look at historically, where are the carbon emissions, more than half of the cumulative emissions have occurred in the last 40 years. So everything that, from the 70s on has really driven that forward. And that's not, the US has been, and other developed countries have been doing it for many years, back into the 1800s or more. But with the growth in transportation and the ubiquitousness of cars and our everything, it's really been driven on since the Second World War. So why do we want to decarbonize? This is likely, in terms of the building sector, the most formidable challenge that we're ever going to see. It's not just individual buildings, it's every building that we've got to deal with. We already are looking at it as 37% of the energy-related carbon emissions, and the building stock is expected to double by 2060. So the huge amount of growth there at the same time. We have population growth, we also have building growth to be able to deal with it. If we're looking at buildings and we're designing them today, our decisions we're making today can lock in an emission level, unfortunately probably high, that will persist for decades unless we are looking at that to be able to really drop it down. So the UN Environment Program estimates that we've got to cut direct carbon emissions by 50% and indirect from power generation by about 60% by 2030. That's only 8 years away, which means we've got to be reducing our emissions by 6% a year over this decade. And that's equivalent to what happened during the pandemic, when everybody stayed home and we didn't have, our buildings were underoccupied. Not that they were unoccupied, but much big change. Unfortunately, that small bump that we had during the pandemic seems to be over, and we're back to where we were before. But if we look at what each of the countries is committed, this starts on the left side. You see a couple countries have already achieved that. Uruguay, Finland are going to achieve it in the next few years. Austria, Iceland by 2040, Germany and Sweden by 2045. The bulk of this is everybody saying, oh, we're going to do this by 2050. And that is going to be a challenge for whatever country is dealing with this. Many of them are trying to deal with a big change in the economy, and you see gaps in Africa. There's no commitment from a lot of countries that are already that are big contributors to this. And then you go over to the far right, and we have China and Australia and Singapore that are not even committing to doing the 2050. And as we saw, we've got to have that commitment to be able to move forward. So let's talk about some basic terminology. Carbon dioxide, it is the gas that everybody talks about, but it is we often talk about it as a carbon dioxide equivalent. The global warming potential of carbon dioxide is 1, so everything else is converted to its global warming potential and then multiplied by that to get to a carbon dioxide equivalent. So global warming potential, again, we're just looking at any other of the greenhouse gases and how their equivalent effect is as compared to carbon dioxide. Greenhouse gases, these are, the ones that are trapping the heat. They're can be natural. It's one of the reasons that we can exist on the planet. We do have a bit of a greenhouse here, but water, carbon dioxide, nitrous oxide, methane, ozone are the primary ones that are controlling that. And for the most part, we are emitting more carbon dioxide and ozone than that would be naturally put in there. But this also includes, the halocarbons and other chlorine, bromine substances that are controlled under the Montreal Protocol as well. So a lot of the refrigerants we use are huge contributors to that, which is one of the reasons they were early things that we looked at. So again, equivalent emissions is just multiplying the global warming potential of a particular a greenhouse gas over its over 100-year lifetime, which for many of them is quite a bit higher. And then I think probably the most important is to understand where the carbon is coming from. And we have operational carbon, the carbon emissions just from operating our buildings. These may be direct, as you see, direct and indirect down there, on-site combustion of carbon, fossil fuels, or indirect is likely the power supply. And so the other important part of this, as we are looking to decarbonize the operation of our buildings, the embodied carbon, the embodied energy related to our buildings is the materials, how we construct our buildings, it becomes increasingly important. So that's something we have to do as well, is find materials and systems that are going to be less carbon intensive as we move forward. Other kind of terminology, life cycle assessment, just looking at impacts of a product, service, or building throughout its life cycle. Environmental product declaration, or EPD. These are independently verified ways of looking at the life cycle information for a particular product. That's a challenge, and as I talk about HVAC systems, unfortunately our industry has very few EPDs for equipment or systems today. There are other things like carbon capture, utilization, and storage, where we try to capture emissions before they get into the atmosphere. Other, site carbon sequestration, and finally building performance standards, which we are beginning to see get traction. The Boston, New York, Washington here on the East Coast are all have set up standards that require that our existing buildings get better over time. So that doesn't mean it's not just a one shot energy performance standard. This is a over the life of the building, and as we move forward, our buildings have to move to zero. And in Boston, that's by the mid 2030s, every building in Boston is supposed to be a net zero carbon building, which is a huge challenge as we're moving forward. So let's talk a little bit about carbon in buildings and how it relates. This is from a European standard talking about all the bits and pieces. The blue is the use stage, but that includes building operation, maintenance, repair, replacement, refurbishment, the operational energy and water related to that. But that's not all that's going on. There's also, the other stages of life, from the product stage, where we're trying to get the materials, transport them, manufacture and bring them to the site, install them, as well as in the life stage, how are we deconstructing, demolishing, and how are we reusing materials or waste? Well, the focus of a lot of this work is in B1 to 7, that use stage there, but there's a huge amount of embodied carbon related to that, and we need to take that into account as we're working forward. And if you look down at the bottom, you'll see scope 1 and 2, which is the operational carbon, and that's what a lot of people talk about. But the rest of it is all scope 3. That's the carbon that's already in the product, in the systems that we're designing, that we've installed, that we really need to deal with. So what do we mean by building decarbonization? Essentially, we want to reduce or eliminate the man-made side of carbon emissions related to building, and doing that throughout its life cycle, not just the operational side, but also the construction side. As far as how people look at it, the kind of 4 pillars for decarbonization begin by reducing the emissions in our materials and systems that we select. Energy efficiency is still very important. Making our buildings as efficient as we can means we're reducing carbon. And then beyond that, using cleaner energy sources, and we'll talk a little bit more about that in a bit. And then finally, shifting to electricity. With buildings responsible for about 72% of our electricity use in the US, buildings consume most of that power generation. And if it's not clean, we're not moving forward.
Drew, did you say 72%? Just then,
Yeah.
72% of electricity.
Electricity is used in our buildings.
It's incredible.
Yeah, there's 30 some that's industry, and then a small percentage for transportation, but our buildings use the bulk of electricity.
Incredible.
So some of the basics, and this is derived, ASHRAE published this past summer a position document on building decarbonization. I'll talk a little bit more about things that position document brings up. We have to continue providing the environments that people want to be in. They've got to be healthy. They have to enhance productivity and be places that people want to be. We already know that we can design, build, and operate buildings that either minimize or eliminate carbon emissions, and that's possible today. There a growing number of buildings, unfortunately, it's not a huge percentage yet, that are already operating at zero energy, but pushing that on to zero carbon is kind of the next challenge. Our HVAC systems, we have both direct and indirect emissions. The electricity is the indirect side of it, but fossil fuel fired equipment is the direct side. So we have to work on both sides of that. Energy is kind of, continues to be the mainstay here, but we also have refrigerants, and our refrigerants, depending on how good the systems are and how well they're maintained, can leak a huge amount, and refrigerants have a global warming potential way higher than that of carbon itself. Again, we have to look at embodied carbon and understand where that's coming from, and understand where the emissions are and where they're occurring, and how we can do that. The International Energy Agency says that it's possible to decarbonize our buildings. If you start there with 2020, by 2030, it's going to see about a 30% growth in new buildings. So we're going to see a big increase. But on the other hand, if we start looking at mitigating that, we could reduce by 2030. We could deal with most of that growth and more by half by 2030. But as we move from 2030 to 2050, we're going to see a doubling effectively of energy use in buildings or carbon emissions, I should say. But at the same time, we have the technology today to take that almost to zero by 2050. So there is a lot of things that we can do, but we need to be doing it now.
So Drew, this leads to a question really related to energy that's coming up in the question panel is, if we move to electrification, which is the argument you're making for the right reasons, away from fossil fuel to electrification, it sort of makes the implied assumption that electrification will be non-fossil as well. And one of the questions coming up is, can renewables meet that challenge? And or what about nuclear?
Yeah.
So can you speak to those?
Yeah, those are great questions. If we electrified every building in the US, the power grid would fail.
Mm-hmm.
We don't have current capacity, and it would require kind of a doubling of current capacity to take it there.
Right.
So we have to, at the same time that we're moving away from fossil fuels, we have to implement efficiency and make our buildings better, taking them as far as we can go reasonably. Nuclear, from a carbon standpoint, is good. Ignoring the issues around what do we do with the waste, but because it effectively is a zero carbon or near zero, there's still energy used to extract the fissile materials that are used in that, and the plants themselves are not zero carbon. So, but it's one of the cleanest sources we have, second to the renewables. But it is a kind of a key thing that we've got to have the renewables coming online, and we are. I mean, it's interesting to watch. As I travel, you didn't used to see, a wind turbine here and there was kind of a thing you didn't see very often. Now, everywhere I go worldwide, you're seeing people using that resource, partly because it's cheaper to put in a new wind turbine or a new utility scale photovoltaic system than it is to put in some of the carbon-based system. And it's not because of regulation, it's just the fact that they're cheaper to operate.
Yeah, one of the points I wanted to make, and I did make in the question and answer chat, is that from a cost point of view, we're currently leading with solar and wind. Solar and wind, in terms of cost per kilowatt hour, is far below anything, including and in particular nuclear. Nuclear has never been cost effective.
No, it hasn't. But just partly because it's a clean source. From an environmental aspect, but still dealing with what do we do with the waste when we're done is
and how do we afford it? None of them have come in on price. As you know, there's only one being built in the United States at the moment. It's way over in terms of cost, and they're not even sure they're going to complete that one because I don't want to go off on a tangent here, but as you well know, you were part of DOE. We never standardized on a design for nuclear, and so they're all sort of bespoke. They're all custom, and as a result, they all run over in cost.
Yeah, that's that it continues to be a real challenge. I mean, even France, where I think it's 60% of their power right now comes from nuclear. Mm-hmm. By 2050 and beyond, they're expecting that to drop to 2030.
Yeah,
there's many of these plants that we built in the 60s, 70s, and so on are reaching end of life.
Yes,
and it's a challenge. Can we recertify them? Can we keep them operating? So, okay. So let's see here. Next slide. Come on. So some of the principles of it, we talked about pillars, but reuse our existing buildings. Try not to take that carbon that we've already captured in many respects in our systems and our building and keeping that on site. So many of the passive sort of things that we're talking about, also making sure our buildings are oriented well, that we've got the geometry done to take care of solar potential. And so taking advantage of what are the opportunities there are. Minimizing the embodied carbon in new construction materials. A lot of people are pushing for a lot of wood products today to be able to do that. But even in wood construction, we have an immense amount of waste of materials, that go in the dumpster that are basically put in the landfill for that. Look at electrifying space and water heating and cooking where possible. Hot water heat pumps are out there. They're a little bit more expensive, but long term they tend to perform a lot better. The efficiency is quite a bit higher. Going with all electric cooking is also something that's being pushed, particularly induction systems. That seems to be gaining some excuse me, some traction in the market. Similarly, in New York City now, you no longer in new buildings or even in existing building, you can't get a natural gas supply anymore. It's against the law to be able to do that in New York. And I think we're going to see that continuing to basically a phasing out of that. So having systems and materials that do that are going to be important. Refrigerants, we've got to move as far as we can toward the low GWP refrigerants. But one of the reasons we use the refrigerants because they're very efficient at being able to transfer heat within our cooling systems, and we need to still keep that in mind. We can't push back to the point there. Where we can put on-site renewables, that's great. If you can't, off-site. And as I show a little later, there are systems now that you can get real-time carbon usage and renewables or removal out of existing systems, which is kind of an interesting technology. Carbon capture is there. And then if you can't do any more within your existing using carbon offsets or purchasing those to offset whatever's less.
Just before you go there, one of the first points you make there, Dru, I think is fascinating. Reuse existing. Now, many would argue that, look, this is a pre-war building. It's made of brick. It's got it's one big thermal mass. It has no ductwork. I'm working on a couple of these. You might be able to tell. Knock it down. Let's knock it down and build a more energy efficient. Now, you got a lot of the guys in the building space encouraging that for obvious reasons, because it's more fun to work on a new efficient building than a dirty old one. So just speak to that issue of reuse existing building for a moment, if you might.
Well, here in the U.S., although globally we're looking at a 50% increase in building floor area over the next 40, 50 years, but in the U.S., 80% of what will be here in 2050 is already here. We are building, but we're not building at the rate that a lot of the developing economies are. So that opportunity to keep that embodied energy that we've already put into our buildings is really critical. So I think the bigger opportunities, and that's what the building performance standards really are pushing, is not so much to tear down what we've got, but to make it better as we move along. So.
Yeah. Okay.
So some of the issues related to decarbonization, if it were easy, we would have already done it. So, buildings are custom. It's one of the challenges we have. There are a few building types out there that are, franchise type sort restaurants and that sort of thing that have a footprint, but even those vary somewhat building to building. We build custom on almost every building we do. I mean, there's some variation there in the housing market as well, but for the most part, there's not an easy solution that's going to work for every building. We have residential, commercial, industrial buildings. A lot of the buildings that we're going to be dealing with are already here, so we have to deal with that existing building stock. Some places that's going to be only 60%, but here in North America and Europe, it's more like 80% are already here. We're dealing with existing generation, electric generation fuel mix. Even if I electrify my building, how clean is that to begin with? And the reality is not many are very clean. Here, where I live in Washington, D.C., we had one of the dirtiest power plants. It was actually across the river in Virginia, but it was supplying us. And they took that offline 15 years ago, and it made our carbon emissions related electricity drop by half just because of how bad it was. But that is, it's not just buildings getting better, the electric grid's got to get better at the same time. And developed versus undeveloped, we kind of talked about that a bit more earlier, and so same time, we have codes and standards particularly related to buildings, but for many places, and you see in the central US, there are not mandatory codes for the state. That's true up into Canada as well. In many respects, there are standards for major cities in those particular places. But if you look at South America and Africa and South Asia, there are many places that don't even have a beginning point for looking at energy efficiency standards. Another big issue is what is the metric we're going to use? For many years, ASHRAE is focused on energy use as kind of the metric for dealing with energy efficiency in our 90.1, 90.2 standards for commercial residential building. That's evolving, and there's a push within the society that what we're going to be measuring and what we're going to be accounting for and pushing toward is carbon, and that's already changing within those standards. But then even looking at carbon, what do we mean by that? Is it average, hourly, historical, forward-looking? Is it based on cost? There are lots of different ways of dealing with that. And then can I buy my way out of the problem? Can I buy an offset? In guides from U.S. Environmental Protection Agency, SIBSI, World Resources Institute, you can do that, but in ASHRAE Standard 228, which is still under development, it's not allowed. So for that standard, it's supposed to be absolute, not trying to buy your way out of it. Do we have a common measurement scale? What are our benchmarks for that? And many of our standards today just include the thermal side of things, and there's a lot in what's called standard 90.1, for example, unregulated loads. We don't regulate the amount of power that people bring in for plugs or other processes. Those are considered, out of the standard, and we need to include that if we're going to truly go to there. And embodied carbon and life cycle analysis, those are big challenges pushed by the green building rating systems that we've seen globally. It's an important part of making sure we have it all covered. But do we have data for it? And the reality is there's not enough data. Europe has decent data sets. We have kind of thin, I will say, data sets because there are big geographical differences in where materials come from. And so having that side of things is really important. Refrigerants, a huge amount. And this is pretty old. And I talked to a friend of mine who works at ASHRAE, and he says that these are probably optimistic in many respects. But if we're looking, our refrigerators at home, it's only 0.1% to 0.5% that we'll lose a refrigerant on an annual basis. But you go down to transport, up to 50% of that refrigerant is lost on an annual basis, or medium large commercial refrigerant up to 30%. So our chillers are not bad. Our residential AC and heat pumps are kind of not bad, but we have a large excuse me, a big way to move.
And when you talk here about transport right there, Drew, are you referring to the transportation of refrigeration, or you're talking about refrigeration in the vehicles that are being transported? What does transport refer to?
In that case, it's like refrigerated trucks.
Yeah, that's what I was thinking. And is that because they fail and leak and, could due to vibration, things like that? Is that what's causing that?
That's a big part of it. It's not like our residential heat pumps that are basically standalone and don't have anything working on the joints and causing it to leak. A mobile refrigeration unit is subject to a lot of stress.
Yes.
So
makes sense.
Other issues, timing of the energy use. The sources and the emissions are time dependent. It'd be great to say the renewables were 24/7, but they're not. We have wind doesn't blow all the time, sun's not up all the time. So we are going to have to deal with that second topic, storage. How are we going to be able to manage that? And there are large steps forward in that. One of the states in Australia, their utility has recently brought online, I think it's 250 megawatt battery packs from one of the large, I will say, car manufacturers. And it's been such a success that they're looking to double or triple that amount, because it means they have instantaneous power available when they need it, and they can charge them when they have an excess of power. Thermal, of course, always a good resource for us, but that tends to still be at a building scale, maybe a small community scale. How do we deal with cold climates? Heat pumps for many years, once you got below about freezing, it was effectively an electric resistance heater. That's no longer true. You can see those going down, that there still has some efficiency down above 1, down in, towards 17 degrees, but that's for a lot of Northern Europe and North America. We need things that are going to operate much better at those temperatures that are, substantially below freezing. How do we deal with the grid? Both understand what the challenges are for the grid, but at the same time be able to react to that. And it's more than just shedding load and being able to do that. Our buildings are not simple. They are, in many respects, a friend of mine at Carnegie Mellon University says, if you look at our automobiles, they have about 10 times the number of control points and sensors that most of our office buildings have today, which means that, there's a lot more information being collected and dealt with there. Now, that is something that we build many copies of the same thing, so they can put the effort in, but our buildings, again, that's an issue. And do we train the people to be able to deal with that? And are we making sure that they're continuing to operate well and doing commissioning and recommissioning of that?
Just before you go there, Drew, the discussion has come up in the question section about storage. Again, we get back to this issue of renewables in a sense, and saying, well, okay, wind and solar is going to be a big part of this because it's non-fossil based. However, we need some capacity to be able to hold the stored energy for use when it's needed. Okay. Secondarily, there's been discussion about time shifting. In other words, pulling power from the west when the sun is shining still to power the evening in the east when it's dark, right? Shifting it, which implicates the grid. So you did
Right.
mention grid, and of course, grid infrastructure is important to be able to shift like that. What about storage, specifically battery storage?
Yeah, well, I think we're going to see a huge change. It's already possible to get a battery storage that'll supplement a renewable system in your home.
Right.
Not cheap at this point. But there is a there is a large opportunity there for that. But I think until we have incentives or beginning to push that technology forward, it's going to be difficult for most people to justify kind of doubling the cost of the renewable system by putting storage in. But on the other hand, I think for utilities that is small scale storage at community level or even at the utility scale is going to really be key.
Just a point for those in New England, Green Mountain Power has been very successful with the deployment of small scale storage into residential homes, and then using that during peak load conditions to aggregate it and pull it and offset the cost of spot pricing on electricity from the grid. If any of you are interested, I can point you to press release. It's pretty easy to find. All you have to do is Google Green Mountain Power in Vermont and energy efficiency, battery storage. They're quite proud of it. And this is, as you just pointed out, Drew, distributed. In other words, instead of having one big load center at a substation where you've got a massive battery, what they've done is distributed into homes and effectively subsidized it, so that for $10 a month, you get in this case, a Tesla Powerwall, 2 of them put in your home.
Yeah.
And they get to aggregate those on periods when they need them. The rest of the time you get to use it. That model is really quite interesting and has shown promise. So to your point, distribution of load, right? Distribution of storage.
Yeah, well, that example I used in Victoria, Australia, they basically have a huge bank of the Tesla batteries. It's just 150 or 200 of those batteries put together to be able to meet the load, or whatever the number is. But it's a huge footprint for them as far as land. So yeah, I think there's a lot of opportunity there. Okay, yeah, I got to move on. I'm behind. So if we're going to go to zero emissions, net zero emissions by 2050, they're kind of things that we have to do. We have to have standards that are already reflecting that. The building performance standards I've mentioned for Boston, New York, and other places, the tools and the training all have to be part of that. But we have to, at the same time, electrify, energy efficiency, have to be looking at grid friendly. So we have the storage and we can have grid responsiveness, both in our buildings, but also at the utility level. And then finally, zero carbon energy, having that available for that. If our buildings can't go to zero unless the grid is zero as well. Excuse me. So this is the building performance standard in Boston. So over the next year, or the next 30 years, depending on building type, you've got to take your buildings to zero carbon per square foot. So for example, office buildings, you by 2034 have to be about 50% better, and by 2044 we're already at 75% better. So by the time we get to 2050, truly zero. And this is part of the regulations now in Boston. Now these are referring mostly to bigger buildings. A lot of these standards don't go below about 10,000 square feet, just because of the onerousness of dealing with that. So these are dealing with mostly commercial at this point, and with half of our building stock still in the larger is still residential, it's going to be a challenge to move there. It does include multifamily housing, but that's not going to cover all the single family housing that's out there. If you look at wind and solar power, globally it's about 1/10 of the global electricity already, and that's pretty amazing what's happened there. But it's the 4th largest source of electricity beyond coal, gas, and hydro, and growing. And in the U.S., 80% of the new, well, it wasn't just the U.S., sorry, it's globally, 80% of new electricity plants that went in are renewable. So that's huge change there. But so if you look at the U.S., it's about 13%, which is a big increase. Less so in Canada, Mexico, Nicaragua, doing better than the U.S. for the grid solar. If we look at South America, 13% for Brazil, 21% for Chile. Brazil has always seen themselves as very much a green power because their baseline is a lot of hydro. And so they have a lot of that, but anything new they've been building these days has had to be fossil fuel generated. We look at Africa, not much penetration there. We have Kenya is doing well at 17%, and Morocco, Mauritania up over 10% there, but huge parts of the country. You look at Nigeria, they're kind of at the elbow on they're only 0.1%, and that's the largest economy in Africa still, and is expected to continue to be. You look, we go to Asia, and China's at 11%. That's growing quite well, but they're little beyond that 10% level, and it really needs to be. China's still building coal-fired plants. India is as well. Australia over 21%, great solar resource, but they have still a large proportion of dirty coal going on there. Europe, though, is doing quite well, and so if you look at UK at 25%, Germany at 28, but Denmark 51%, and occasionally I'll see a news item. UK completely ran on solar today, or Germany was 100% renewables for this day, and so that's beginning to get there, but it doesn't happen all year yet, and that's kind of a challenge. But we are seeing big opportunities there. There are ways to get rid of the carbon once we've emitted it. We can try to restore it back into the ocean. Actually, the ocean is one of the big largest places that carbon dioxide actually gets dissolved into seawater and precipitates out. We can try to put it back into some of the mines that we put there, or also even just looking at doing it at the power station itself rather than letting it get emitted. One of the biggest sources of carbon storage, of course, are forests. And 10,000 years ago, about 57% of the land area was forest. By 1700, that had dropped to 52%, but we had crops coming in, we had grassland, and some urbanization, but not as much going on there. By 1950s, that 52% had dropped to 44%, and the grazing area has grown from 6% to 31%. So we're now, for food production and crops, we're now almost half of our land area is covered by that. And then by 2018, we're now looking at truly 50% for grazing and crops, and the forest has dropped to 38%. Well, as a resource, a place to store carbon, that's really an important part of what we're able to do. So there are different ways of dealing with this. Dealing with the sequestration, we can store it. We can use CO2 as a fuel. We can capture it through our forests, reforestation being a big opportunity there, or using it in other chemicals. And there are lots of different ways of looking at it, but it's, for buildings, it really is, can we do something in our concrete and our HVAC system? Because concrete is one of the more energy and carbon intensive materials that we use in our buildings. Here's an example. This is a company that has a viable product, but they basically will come in and capture the carbon so that it's not going out the chimney from boilers, and they'll store it and then cart it off site for sequestration. So there are technologies to be able to do that today, but cost is still an issue for that. So I mentioned whole building life cycle analysis earlier, but really it's just a way of quantifying what's going on as far as the environmental impacts of buildings and processes. It really is the best way to look at any carbon emissions for any building project, really. We're already seeing it show up as an opportunity in many of the green building rating systems that are, they talk about using LCA as an alternate to try to do the accounting that a lot of projects do today to try to get the points in those rating systems. But it looks specifically at the global warming potential, acidification, eutrophication, ozone depletion, photochemical ozone creation, abiotic depletion, and for fossil resources. So it is looking the spectrum of what's happening to the environmental impact and trying to quantify that for the building. Why bother? Well, this is not unlike a chart that I show when I'm talking about energy modeling. The sooner we do the analysis, the more impact we can have. By the time we're through design, we've lost about 2/3 of the potential savings that can be done. So, looking at those opportunities really is important to be able to do early for that particular case. So LEED does give you up to 3 points for doing an LCA and reducing the carbon of the structure and enclosure. Living ILFI, zero carbon certification, same sort of thing, is reducing the embodied carbon of that kind of key parts of the building, the structural parts. BREEAM, very similar sorts of things. There are tools available. There's the ICE, which is UK. There are Quartz, which has got 100 generic products, so they're not going to be very specific to company. Carbon Designer, which is one of the early design tools that you can use, and a product called One Click LCA, which I'm seeing embedded or linked to in a lot of the BIM tools today. Construction Carbon Calculator is kind of generic so that you can give some information, and it'll give you good, decent, I will say decent, it's not detailed. Eco Calculator, another kind of early look at that. Other tools, Athena Impact Estimator, Athena being a group out of Canada, has been developing data for that. And so they have that life cycle inventory data they've been doing for Canada and the US. One Click LCA I mentioned. Ability to increase detail to be able to look at it. Tally, another BIM tool, and the embodied carbon construction calculator as well. That has interesting because it gives you access to the construction EPDs, which we mentioned briefly, but talking about that, the EPDs, this is kind of an easy way. If I know what the impacts are of a particular material or product, and I have a verified way of looking at that, then I can definitely get more. I can put these LCA together better. But there's standards related to that. These databases I've just talked about are trying to pull all that information together, but we need that. Unfortunately, most of the equipment that we put in our buildings, our MEP equipment, doesn't have an EPD. There's not the data available. There are many sources for the materials there, and so it's difficult to get some of that information. Let's see. Yeah, I'm running long. Sorry, guys.
It's okay, Drew. You don't have a flight to catch, so it's all right.
No, I don't. But other people may need to go to work.
I understand. Yeah.
But to do LCA, we need to know what we're trying to do, collect the inventory of information, do the assessment, interpret the results. Unfortunately, that collecting the information is the hardest part, and where we have missing data today. So that still is a challenge. From the building side, we're looking at fossil fuel powered equipment that we're putting in today, and what can we do? Lower GDP refrigerants, green fuels, including hydrogen as a possibility, renewable gas, methane recovery, biofuels, cooking oil. Those still do emit, but they're not adding to the problem that they were already there. Heat pumps, and unfortunately, what you're hearing, the mantra for a lot of the industry right now is heat pumps, heat pumps, heat pumps. And I think heat pumps are an important part of it, but there are other things that we can do there. As far as lower GDP refrigerants, we see global warming potential there from R410A is 2,088 times the amount of GDP as carbon dioxide. And so if we move away from those toward the lower global warming potentials, you see the HFOs and R514A, we're also seeing kind of a safety issue. The traditional ones we've been looking at have been pretty safe to use. You don't have to worry about flammability or other things. And as we move towards some of these others, the B1 category is definitely can be dangerous, and the exposure limits are much lower. So we have a leak, it can be dangerous for people to be in the space. I feel silly talking about heat pumps to an ASHRAE audience, but there are a lot of different types. We probably think of heat pumps as kind of our traditional one in our homes, but different sources: air, water, ground, solar, or even industrial scale. And today, though, we are seeing everything from residential appliances to industrial scale heat pumps. So that technology, is pretty straightforward. It can be easily done. So the traditional kind of ones we see in our buildings today, but also looking at the things like a heat pump water heater. Instead of having electric resistance, we can get an efficiency 2, 3, 4 times what we could with compared to that electric resistance. And one that my wife and I are about to try is a heat pump dryer, and it effectively has no vent, so it's ventless. You don't have to worry about hot air or hot moist air coming on. What comes out of that is water that just goes down the drain. They're just using the heat pump to dry out the clothes. The 2020 handbook has a great comparison of the different HVAC systems, particularly the heat pumps, and their sources, heat sinks, costs, temperature, and where they're typically used. So it's a great table here related to that. As the grid is transitioning to renewables and clean fuels, we talked about renewables earlier, but we're essentially talking utility scale. And I worked 30 years ago at a electric utility in California, and even at that point, wind and solar were the cheapest new generation capability they had. And today, the price is a tenth of what it was. So for them, it's kind of a win-win, because they're getting cheaper installation, but at the same time they have to deal with storage. And how are we going to deal with time of use versus availability? And that's really lots of people have been dealing with that for many years. Pump, hydroelectric, and other systems there. Renewable hydrogen, hydrogen-infused natural gas, biogases, trying to recover some of those and use them before they're offset. Methane's a very potent greenhouse gas, so if we can capture it and use it before it gets into the atmosphere, we're better off. We have changed our electricity generation. We kind of peaked out in the U.S. With coal in about 2007, 2008. A lot of that transition happened because natural gas was relatively available and cheap. But we're also seeing, nuclears is a big part of it, and renewables is a growing part of it. So that's interesting transition that's already underway here. Worldwide, by 2050, wind and solar is going to make up more than a third of the generation, with hydroelectric nuclear taking it well over half. So, coal and natural gas, coal is not going to be growing, but still will be a baseline for us there. But you see there, the net generation by solar will be the largest source by 2050 and growing, exponentially. Coal has been, 40 countries have talked about phasing it out. Unfortunately, if you look there kind of in the middle of the chart, you see the rest of the world has been kind of up and down, but not growing. But China, on the other hand, in the last 20 years has quadrupled the amount of coal that they're using. And so that is having that. So, but if we really are trying to take it to zero, we've got to be dealing with the coal from the beginning. But we've done it before. Prior to the Industrial Revolution, we were basically human power and biomass. So as we move to middle of the 19th century, that's where we get our first oil. By 1930, though, coal is a very efficient way of being able to generate power, and that was kind of predominant for many years, still is. And then by 50 years ago, we were looking at oil demand, partly because we're now it's the best way to power our vehicles, and not the best way, but a very efficient, cost-effective way of doing it. So that by the time, by this decade, we're looking at 80% of the global energy mix are fossil fuel related. So we've been able to transition, and we'll continue doing that. So the International Energy Agency has a roadmap, and I'm just going to point out a couple of the things. So by 2025, no fossil fuel boilers. All new buildings by 2030 are zero carbon ready. Appliances are best in class by 2030. 50% are zero carbon ready by 2040. Heat pumps are meeting 50% of the demand, and 85% of the buildings are zero carbon ready by 2050. So I want to talk a little bit, and kind of giving you the background, but let's talk a little bit about what ASHRAE is doing. ASHRAE is the standards authority globally, really, for a lot of things related to energy performance uses. And our standards are already thinking about carbon, and not all of them are really moving there, but I think that's going to change pretty radically in the next few years. The board has directed a number of the standards that is the way they're going. We already have guides on how to get to better buildings, best practices, guidelines, benchmarking, etc. And we have members in 130 countries. So we do have global reach. So there was a position document that was published this past summer. And these are kind of key things. And I've talked to many about them, but we'll go to the middle. By 2050, all new and existing assets must be net zero emissions across the whole life cycle. That's kind of a key part of that. So ASHRAE is, putting a stake in the ground to say where they're going. And at the same time, committing to looking at, making decarbonization a focus in our research, our standards, design and equipment, technical guidance, any guidelines and measures, and educational resources. We talked about the carbon reduction principles. They're pretty much the same we mentioned earlier. The decarbonization strategies, we can decarbonize any building. It's not dependent on age or anything else. We can deal with that. LCA is a critical part of that. New buildings are probably going to be easier for us. We can do that quicker. Retrofitting the large number of buildings, and I think building performance standards are going to be the key for that. The best practices can significantly impact the emissions, and so how we use our buildings, how we operate them is really key. And probably most important is that we can't really sacrifice the health and resilience of our indoor environment. That, we're not building buildings to be decarbonized. We are creating them as spaces for various places. So the challenges, we've already talked about this: cold climates, electric grid, return on investment being a challenge. Most people who own buildings, that's not their main business, so they're looking for higher return on investment than they might from their business. Historic buildings, no mandatory energy performance standards globally, and electricity and understanding how its carbon is, which is kind of key for that. If you look at the ASHRAE standards, and I'm not going to go through this in detail, but traditionally we focused on the energy efficiency, beginning to look at some of the carbon. Haven't really been looking at embodied carbon very much. Some of our standards are just around efficient emissions related to refrigerants, and then of course renewables. So we don't have standards that are really pushing that. Now there's a new standard that's under development, 240p, which is looking at greenhouse gases and carbon emission, and intended to pull all of that together to be able to be kind of the baseline standard that can then be referenced by all our other standards. The task force for building decarbonization, there was an initial one started in 2021. It got a lot of work done in publishing information, collecting information, and the new one which started this past July, much more trying to push that out into technology. I'm not going to go into all of this, but really trying to take the resources that have been developed and move that forward. They are by the end of June 2023, there are to provide a comprehensive plan for how this gets put into all of ASHRAE structure, the technical committees, the standards, etc., and be able to move that. And coordinating that activity instead of a standalone task force, which is where it's been before. Society's strategic plan was actually delayed by a couple of years, partly to be able to work with the planning committee to make sure that these goals got in the strategic plan, because that plan's only updated about every 5 years. So that sort of piece is there. But one of the key things of their doing, that this task force has been doing, is working on a knowledge hub, pulling together the technical resources, standards, education, and training into a single place, a single point on ASHRAE's website to be able to pull it together. So all the things that we're already doing and things that are already underway. The task force is really broken into two parts now: an operational subcommittee, and essentially they are developing 6 guides for decarbonization retrofit, heat pumps, healthcare, building performance, grid interactive buildings, and whole building life cycle analysis, so that being able to deal with that. The products and services committee is working on the other side of things. So In conclusion, the buildings are responsible for, depending on the numbers, and I probably should make this 37%, but it's in the range of up to 40% of our carbon emissions globally are related to buildings. Anytime we build a building, we're locking in emissions at that level. Can be high if we're not paying attention to it for decades to come. Buildings don't, it's not a service that is a short-lived. When we talk about decarbonization, we're still talking about efficiency, but also cleaner sources and moving toward low carbon electricity for that. As we take our buildings to zero operating energy, that embodied part becomes more important. The good news is I think we have some time to work on that. We have a lot of work to be going on the operational side first, that we can work on finding solutions to making sure our buildings are low embodied carbon for that. The task force from ASHRAE is really a great resource to being able to deal with a lot of this activity. ASHRAE had earlier this month a building decarbonization conference, and that brought people together from 30 countries to be able to talk about activities there. A lot of interesting papers related to that. As the task force research and knowledge hub is really where that task force is going to be pushing that information together and pulling it as kind of a resource for the membership. So with that, I'll happily take any questions.
I think the first question, I think for us in the United States here, focused on this sort of locally, is how do we best decarbonize existing structures? What are the steps we need to take to improve the situation on existing building stock? I would think, right? I mean, isn't that really where we need to focus?
I mean, it's 80% of the problem, or more, because our new buildings tend to be a little more efficient.
Right.
And so I think we need to start with what can we do to make them more efficient? Are there retrofit opportunities we can take forward on that? Is it a source issue that we can electrify?
Mm-hmm.
What level of renewables can we provide?
There? Yeah. Mm-hmm. And can we use storage as a way to?
And storage is a way to bridge when we don't have the renewable resource. Yeah.
Now, there's been a discussion here about ROI on those things. The issue with ROI is always, of course, that first of all, you're focused purely on the economics and not the impact that the right. I mean, if you took into account the return with respect to global warming, it would be a different calculation.
Right.
But do you have any advice on how to handle the traditional economic ROI argument with respect to the fact that, hey, guess what? This retrofit's if I bought a fossil-based boiler, it's going to be a hell of a lot cheaper than a heat pump. So what's my ROI? How would you recommend we handle that?
Yeah, that's kind of in my work over years doing consulting and everything. I've been very frustrated. We present to owners and we say you can get a 20-30% return per year. And they go, I don't think I can take the risk. And it took me a while to understand that in their business, they understand all the risk and the opportunities, but as a building owner or operator, it's a container for their business, not something that they know a lot about. And so the uncertainty related to that, for them, is a lot higher than a 30% return. And that's a big challenge. But man, if I could find 30% return for things I'm doing, I'd love to right now.
Right.
But it's kind of trying to take the risk out of that opportunity is really the biggest thing. Showing people this is not rocket science. This is something that your competitor down the street's already done, or the utility is going to help you by giving you incentives, or their federal incentives for some of this to be able to take some of that risk out. And so I think that's really, it's kind of an education on ROI opportunity. But if I'm a mom and pop shop and I'm trying to sell my bagels, or bookstore or whatever, the building side is in the noise for them. It's a cost. They don't really see that as an opportunity. So it is a challenge to be able to convince people.
Well, the other point we can make most obviously right now is the energy cost is going to continue to rise, and the most recent increases caused by our friend Putin in Europe that has disrupted the entire global energy supply system is indicative of the uncertainty of being dependent upon things like fossil fuel.
Right.
Not that electricity isn't still dependent on fossil fuel, but at least we have a plan to get away from fossil fuel and electricity generation, and so it's a better bet than being dependent on fossil fuel for heating of your own facility.
Right, and decarbonizing that's also going to take a lot of the risk out of the electric grid as well, because we're still 50% is still dependent on natural gas or other sources that may be from out of the control of our country, and that's kind of a challenge.
That's correct. Yeah. Well, listen, Drew, we've run over by 30 minutes. I appreciate your extra time here today. We've been able to hang on to most of our audience. We had well over 20 people attending today. I think we're up to 24. So I want to thank you for this really informative presentation. This is a challenge for us all. This is the beginning of the beginning, in a sense, for us to try to get to the point where we can drive down the consumption of our buildings and their relative impact on carbon contribution. So I want to thank you for taking the time to be with us on this webinar. And for those of you in the audience, I will have a set of Drew's slides that I will put with the thank you email that comes to you. And if you don't get them that way, just reach out to me and I'll have a copy I can provide to you. Thanks, Drew, for your time.
Great. Thank you very much.
Have a good day.